Now, we would like to ask a converse question to the lemma 5. Suppose you have a vector that is orthogonal to z for any z in lambda with a very small norm. Then, do you have that vector living in M? So let me write it down more carefully. Suppose that there is an epsilon 1 greater than 0 and a vector lambda 1 through lambda m in Rn such that whenever z is in lambda and the maximum norm of z is less than epsilon 1, we have lambda is orthogonal to z. Another question is lambda in the z-span of u1 through us, which is m? I'll let you think about it. So the answer is no. The answer is no because if we take the m by n matrix A to be the zero matrix, then lambda, which is by definition AQ minus P, where P is in Zm and Q is in Zn, will be simply Zm. And it follows that any z in lambda, which is Zm with maximum norm less than 1/2. Here we are taking epsilon 1 to be 1/2. Any z satisfying this must be 0. So, any lambda in Rn is orthogonal to this 0 vector z. But lambda is not in z-span of u1 through us. If we take, say, lambda to be the vector whose maximum norm is strictly greater than 0 but less than the minimum of those vectors in M that is non-zero. We take the minimum of the length of vectors under the maximum norm that is non-zero, where the vector is in M. And it follows that this lambda cannot be in z-span of u1 through us, which is precisely M. So, the lambda is not always in the z-span. But we have lambda is in the R span of vectors u1 through us. Namely, R is in the plane, the smallest vector subspace over R containing M. And this will be our lemma 6. And let's call it the lemma of converse rigidity. So the text in black will be the statement of this lemma. Let us start with the proof. The idea of the proof is the following. We'll try to simplify the hypothesis on this lambda. So here, lambda is any vector in Rm such that blah blah blah. And we want to reduce the proof of this to a special case when lambda only belongs to a certain subset of Rm. And the step 1 of the proof will be like this. Will be reduction of this lemma to the case when lambda is a rational vector, namely in Qm instead of Rm. Now, for any epsilon greater than 0 less than epsilon 1, and any z in the subset of lambda whose elements have maximum norm less than epsilon 1. By our hypothesis, we have the lambda is orthogonal to z. And now let us recall the asymptotic version of the Richless homogeneous defining approximation, which states that there exist infinite many P in Zm and Q in Zn minus 0 with GCD of all the components of P and Q, P1 through Pm, Q1 through Qn equal to 1, such that the maximum norm of AQ minus P is less than 1 over the norm of Q raised to the power n over m, where this norm is also the maximum norm. And we can make the norm of Q arbitrarily large. This is the asymptotic version of the Richless homogeneous defining approximation theorem. To confess that I always forget this P in the spelling. So in the application of this theorem into our case, we are not going to use this power. We're just going to use the fact that the norm of Q can be arbitrarily large, so that this guy could be smaller than any given epsilon. We are going to use this Derivation Theorem for the following special case. Take n equal to 1 above and let the matrix A to be the m by 1 matrix, which is really a column vector Z. So this is a m by 1 matrix, and I should say A here is taken from the statement of a Dirichlet theorem, not the Kronecker theorem. And by the Dirichlet theorem, there are W a non-zero integer and T a vector with m components, such that if you look at the maximum norm of Wz minus T, this guy is less than 1 over the norm of W, which is the absolute value of W raised to the power n over m. If the absolute value of W large enough so that 1 over this power is less than epsilon, which is less than epsilon 1. Hence, the maximum norm of Wz minus T is less than epsilon 1 for some choice of W and T. And thus, by our hypothesis says if you have a vector in lambda such that the maximum norm of it is less than epsilon 1, then this vector is orthogonal to lambda. So now we have the norm of this guy is less than epsilon 1. And I should say, moreover, this guy is in lambda. This is because this W and T are both integer valued. And this Z, our assumption earlier, is taken from lambda. So this combination Wz minus T is also in lambda, simply by the definition of lambda. Remember, lambda contains all the integer vectors in Zn. So, with those two conclusions, we can use the hypothesis to get lambda transpose times Wz minus T equal to 0. But we already know that the first part from here, namely lambda T Wz, which is equal to W times lambda T times Z, is 0, which implies by the fact that W is not 0, that lambda T times Z is equal to 0. So, lambda T times T is equal to 0 by looking at those two parts. And I should remind you that this guy is taken from here. we took z so that lambda t z is equal to 0. So this follows from above.